So we've got a random variable d, which is the diameter of a bolt manufactured by a machine. And before a service, we know that the mean diameter is 0.580. And we're asked to test whether after the service, the mean has changed from 0.580. And you can see why you might want to do this, because you might want to go back and reservice the machine if the machine has somehow changed the diameter of the bolts that it's making, because that would be a bad thing. So we don't need to define a variable because the random variable d has already been defined for us. So we're going to write down what distribution d follows. So the diameter of the bolt is normally distributed, and we don't know what the mean is. So we're thinking about what's d after the service. So let's say that's mu is the mean diameter of the bolt after the service. And we're told that the standard deviation doesn't change, so it's 0.015 squared. And here I'm just going to write down what mu is. So mu is the true mean diameter of the bolts after the service. And let's write down what h0 and h1 is. So our null hypothesis is that the service has had no change on the bolts. So that means that the mu after the service would be the same as it was before, which is 0.580. Now we're asked to find whether there's evidence to suggest that the diameter of the bolts has changed. So our alternative hypothesis is that the diameter of the bolts is now different to 0.580. And notice that it says changed, so that means it's going to be a two-tailed test. We're not bothered whether we think the diameter's gone down or the diameter's gone up. We're just testing whether there's going to be a change. So the data that we've got to try and support H1 is the random sample of 50 bolts. So we've got a sample of size 50. And this sample would be D1, D2, all the way up to D50. That's the first diameter of the bolt that I sample, second diameter, all the way up to the 50th. And the data we've got is we're going to work out this sample mean, which we're going to call D bar. So D bar is the sample mean. And it's worth working out what values of D bar, the sample mean, are going to try and support H1. So what values of D bar would we need to see in order to suggest that there has been a change? So because we're just bothered about whether the diameter has changed from 0.580, if we had a sample mean which was much bigger than 0.580 or much smaller than 0.580, then we could conclude that there's been a change. So let's write that down. And by small values here, we mean if D bar was less than 0.580 or if D bar was greater than 0.580. And obviously, the smaller D bar is, or the larger D bar is, the more confident we can be that the diameter of the bolts has changed. For example, if I saw from my sample the average diameter was 0.9, then I could be fairly confident that the diameter of the bolt has changed after the service. So in this in part A, we're asked to find the critical region for the test. So they're going to force us to use the critical region method. So let's have a look at how to find the critical region then. So with the critical region method, we're going to assume that H0 is true. And so we could say under H0, we need to write down what is the distribution of D bar, because that's the data that I've got to try and support H1. So we're going to use the fact that D bar is going to follow a normal distribution. The sample mean is normally distributed. And if H0 is true, then the sample mean is going to have a mean of 0.580. That's when what mu is equal to when H0 is true. And the variance is going to be the same as the variance of D, so 0.015 squared, but then divided by the sample size, which is 50. So here I've used the formula that d bar follows a normal distribution, mean mu and variance sigma squared over n. Sigma squared over n is this part here, and mu, the value of mu that I've used is the h0 value of mu, because we're assuming that h0 is true. So let's draw out what this distribution looks like. So on the horizontal axis we've got d bar, and we can draw out this normal distribution curve that looks something like that. And we know that in the middle, if h0 is true and the machine hasn't changed, then the distribution is going to be centered on 0.580. So we've got to work out what values of d bar are going to be in the critical region. Well, because this is a two-tailed test, it's a two-tailed test because either small values of d bar or large values of d bar mean that we are going to support h1 and reject h0. So that's what makes it a two-tailed test, because we've got not equal there. So small values of d bar are going to be to the left, so somewhere here. And large values of d bar are going to be somewhere there. And actually, if we're in this region, then we're going to conclude that the service means that the machine makes bigger bolts. And if we're in this region here, then we can conclude that the machine makes a smaller bolt. So we need to try and work out what this critical region is. So let's call this value here C1 and this value C here C2. Now we need to look at our significance level, which is a 1% significance level. So because we're splitting this 1% up into two regions, we want no more than 5%, half a percent in each tail. So let's write that down, 0.5% in each tail. Now with the binomial distribution, we'd have to do a bit of trial and error to work out what value of our distribution would be in the critical region, in the tail. Well, with the normal distribution, we can find an exact value of C because it's a continuous distribution. So it's actually a bit easier to do a hypothesis test with the normal distribution. So let's find C. We know the probability of D bar being less than C1 has to be half a percent, so 0.005. So let's use our calculators to work out what that is. So we're going to go to inverse normal, distribution, normal, inverse normal, and for the left critical region C1, we know the probability to the left of us, and we know that probability is 0.005. So we're going to go tail is left, because that's the left of us, 0.005, and we need to put in our standard deviation. So careful, we're doing this with, that should say d bar, we're doing this with d bar as our distribution, and this is the variance of d bar. So this is the variance, and our calculator wants the standard deviation of this distribution. So we need to square root the variance. So if we square root the variance, we're going to have that square root the top, square root the bottom. So we just need to type in 0.015 divided by the square root of 50. Or you could work that out in advance. And mu, under H0, our mean of our d-bar distribution is 0.580. So we're going to get our critical region is 0.5745. 0.5745. And we could do a similar thing for the upper tail, or the right tail. So we know that this area here needs to be 0.5%. So the probability of d bar being greater than C2 is 0.005. So again, we can use our calculator to work out what that is. And all I need to change actually is we want the probability to the right of our unknown value is going to be 0.005. So just change that to right and leave that as 0.005. So if we work that out, we get 0.5855. So now we can write down what the critical region is. So our critical region is D bar needs to either be less than 0.5745 or D bar can be greater than 0.5855. And the reason why we can reject H0 if we're in this region is because it's really unlikely to be in this critical region if H0 is true. So if we land in this critical region, we conclude that this distribution is probably wrong because it's so unlikely that I would land here. And in the final part of this question, we're told that actually when someone goes out and takes a sample of 50 bolts, it's calculated, D bar is calculated, the sample mean, as 0.587. So we want to comment on the observation in light of the critical region. So we're basically doing a hypothesis test. Well, if we look at our diagram that we drew before, we're basically going to work out, is D bar in our critical region? And 0.587 would be somewhere here. So 0.587 is in our critical region because it's bigger than this value here. So let's say that 0.587 is in the critical region. So this basically means that it's so unlikely that I would land here that we must conclude that it seems sensible to say that this distribution is wrong because it's so unlikely that I would land there. So it's in the critical region, so we're going to reject H0 and we're going to say there's evidence to suggest Now, you might be tempted to say evidence to suggest that the bolt diameter is bigger because we're in the right tail. It's bigger than 0.580. Now, we can't do that because we set up this hypothesis test for this alternative hypothesis. So in your conclusion, you have to match the alternative hypothesis. So all we've got is evidence to suggest that the diameter of the bolts has changed. We can't say that it's increased. So evidence to suggest that the mean diameter of bolts has changed after the service.